Hello everyone. Hello everyone and welcome to the PCD for TLE Eliminators post-concert discussions for Codeforces Round 1039. This is Vibhaas Srivastav and I'll be taking your PCD today. We'll be discussing problems A to E1. Okay, A, B, C, D, E1. How was the contest, guys? Okay. How was the contest, guys? Bad? Okay. I felt like it was on the easier side. I started the contest pretty late, so I did not solve from my main. Yeah. Right. All right. We'll discuss all the problems one by one, I guess. I felt the questions, I don't know, I felt the questions were on the easier side, but looks like it wasn't that easy. Um, okay, let's get started. The first problem is recycling center. In a recycling center, there are n trash bags. Ith bag has weight of AFI. At each second, two actions will happen. Choose a trash bag and destroy it. It will cost 1 coin. If the weight of the bag is greater than C and 0 coins otherwise, then the weight of each remaining trash bag will be multiplied by 2. What is the minimum number of coins you have to spend to get rid of all trash bags? Okay. Um, N is up to 30 only. C is up to 10 to the power 9 and AFI is up to 10 to the power 9. Okay. So let us understand what this question is asking us. It's basically saying, so C is the limit beyond which if it's below that, it will take 0 coins. If it's bigger than that, it will take 1 coin, right? So let's say our array of trash bags was something like 1, 2, 3, 4, 5, 6. And let's say C is 4, right? So then everything which is less than equal to 4, right? So these we can remove or destroy these trash bags with a cost of 0. Meanwhile, which is greater than 4, it will take 1 coin to remove these trash bags. Correct? That much makes sense. I didn't feel it was number theory heavy. It was pretty logical today's contest. I thought today's contest was very nice, at least for me. I wish I had done it from my main, but I had gone out, so I started it a bit late. Anyways, so the idea for problem A, right? The idea for problem A is pretty simple. Okay. So the first thing we have to observe, right, is if the trash bag's weight is already greater than C, right? If the trash bag's weight is already greater than C, then no matter what we do to remove that trash bag, it will still cost us 1 coin, right? No matter what we do to remove this, it will cost us 1 coin only, right? Because even if we remove it at the second step, the weight will become 10, or if we remove it on the third step, the weight will become 20, right? Basically, it keeps doubling at each step. No matter what happens, the cost will always be 1 to remove one of the trash bags which are already greater than C, right? Now for these, what can happen is the cost can be 0 or 1 on the basis of when we remove it, right? The cost can be 0 or 1 on the basis of when we remove it. So here, basically what we need to see is which one should we remove first, okay? So what if in the first step, we remove this trash bag, okay? Now the rest all get doubled, right? So this becomes 4, this becomes 6, this becomes 8. Now the thing is, since these are doubled, right? We can no longer take them with only 0 coins, right? So maybe if our array was something like this, then this would be a massive mistake to take 1 first, because 1 has been taken and the cost has been 0 now. But now these are doubled, so we cannot take them for 0 cost, and we will have some cost of 1 coin to take these, right? So for example, my array was equal to 1 3 4 5 6, right? My array was equal to 1 3 4 5 6, and my k is equal to 4. Then in the start I can choose any one of these, but what if I chose one, right? And what if I chose one? What's going to happen is basically the array is going to become 6 8 10 12, right? Now I can no longer choose anything, and to pick the remaining it will take a cost of 4, right? To pick the remaining it will take a cost of 4. So what is the idea here? Okay, so the idea here is we should take the largest one which we can take first. Okay, so always take largest. So it's a greedy idea. Problem A was greedy. Always take the largest bag, largest value less than or equal to C at each step. Okay, at each step. And this is the solution to the problem A. And why are we always taking largest? Because if we take anything smaller than that, we risk losing some elements which have become doubled and no longer being able to take them. Meanwhile, if we take the largest element, if we always take the largest element, then the doubling will only happen to the smaller ones, right? Doubling will only happen, matter in the smallest one, in the smaller ones, matter in the smallest one, in the smaller ones. So if there is still a smaller one remaining, we can take that. If there is no smaller one remaining, that means no matter what we had done, no matter what we had done, it's always best to, like, we would only get one answer, right? We would only be able to take one die. So basically the main idea is always take the largest one, because we just showed, like, if you see this example 1 3 4 5 6 k equals 4, if you take one over here it will be a mistake. The idea is to take 4 first, then we can take one which has been doubled to 2. Okay, so we always take it largest first. Okay, so that's the core idea for problem A. So there are two ways to write it. We can write it in a big O of n approach. We can also write it in a big O of n log n approach. Okay. So sorry, we can write it in a big O of n squared approach as well as a big O of n log n approach. Okay. So the big O of n squared approach is simply in your vector, find largest element, which is less than equal to C. Remove it, double the remaining elements. Okay. Double the remaining elements. Okay. And the answer will be the count of the elements which are greater than C finally. Okay. So the answer will be count of elements once this process is over. Okay. Once this process is over, and you can show that this is an n squared complexity solution. But obviously we'll discuss the best solution, which is n log n. So we'll discuss big O of n log n solution based on this greedy idea. And the idea is simply first we sort the array. Okay. Sort the array. Okay. Now what we have is basically, let's say our array is like 1 2 3 4 5 6 7 8 9 9 10. Okay, and our k is 7. Let's say our k is 7. Okay, so what happens is we will go from array from descending to we'll go through the array in descending order. That means largest to smallest. Iterate largest to smallest. Okay, we have to iterate largest to smallest. Then if this current value, it is greater than k, if the current value is greater than k, then we simply need to add 1 to our answer. We can do answer plus equal to 1, right? So here 10 is greater than k, so we can add 1 to our answer. Similarly, 9 is greater than k, we can add 1 to our answer. Not k, c. In the problem it's written as c, right? So greater than c. Then if again 9 is greater than c, so our answer becomes 3. 8 is greater than c, so our answer becomes 4, right? Our answer is 4 now. Now when we reach 7, the answer becomes just equal to this, right? It becomes just equal to 7. So what we're going to do is we don't need to add a sum. Since we're always removing the larger one, um, since we're always removing the largest one, what we need to do is we can count that we took with 0 coins. It took 0 coins to remove this, so our answer remains the same. But what happens is everything ahead of me gets doubled. Okay, everything ahead of me gets doubled. So basically this will become like 12. This is going to become 10, 8, and so on. So obviously we can do this in an n squared logic, but we don't need to do an n squared logic. We can just have a variable called double maybe, which we can multiply by 2. And that will tell us that all these variables should be multiplied by 2, right? So next time we go to 6, instead of seeing it as 6, we see it as 6 times 2, which is 12, which is greater than C, okay? Similarly, 10 is greater than 7 here. Similarly, 8 is greater than 7, right? Now here we can see that 6 is not greater than 7, right? 6 is not greater than 7. So again, we don't need to add the cost for this variable. Again, we don't need to add the cost for this variable. And here the double becomes 4. The double becomes multiplied by 2 again. So these values will get multiplied by 4, okay? So 2 into 4 is 8, which is greater than 7. But 1 into 4 is 4. So no cost will be taken here as well, right? No cost will be taken here as well. So our final answer will be 4 plus these ones had costed and this one had costed. So 4, 5, 6, 7, 8. So the answer for this test case will be 8. So I hope you understood this logic. We're just sorting the array, going from largest to smallest. Whenever the current element becomes less than or equal to C, it will take no cost. Otherwise, it will take cost of 1. And if it takes no cost, we will double all the future elements. Okay, we'll double all the elements smaller. And what is the approach over here? The approach is simply we are taking the approach is basically based on this idea. It's always optimal to take the largest value less than equal to C at each step. That's what it's based on. Okay, this is the n-log-n approach. If you find an n-squared approach simple, you can implement that. Since in the given question, n just goes up to 100, right? N goes up to 30. So almost any approach will work and goes up to 30. We can do it in O of n with hash map. I guess you can use O of n. Okay, right. So before we go any further, I just forgot to mention TLE self-paced courses are out right now, right? If you haven't seen it before, then do check out TLEeliminators.com/courses, where the courses are divided into 3 levels. So, for example, if you struggle with the first question, I would say level 1 or level 2 of TLE will be for you, right? Where we learn basically greedy algorithms, right? In maybe level 1, I guess. And yeah, the benefits of the course are more than 40 hours of recorded lectures, more than 100 practice problems, hints and video solutions, as well as doubt support. So, like if you feel unfocused or unstructured in your CP journey and you want to bring some structure in it, you want to bring some regularity, do check out the course. It's on sale for the next 4 days, right? So do check it out at eliminators.com/courses. The question tells when you pick a bigger element, you will double the other elements. Yeah, that's what we are doing. We are assuming that the other elements are doubling. But the thing is, no matter how much it doubles, it will only cost 1 coin only, right? At most, it will cost 1 coin. Either it will cost 0 coin or it will cost 1 coin. So even if the element gets doubled, if it was already costing 1 coin, it is still going to cost 1 coin only. Do you understand? So if it is already greater than C, if it doubles, it's still going to cost 1 coin only. I hope that makes sense. Okay, let's move on to problem B. I think this problem was simple enough. So yeah, I think it was slightly harder than the average problem A, but not too much harder. Okay. I don't know why problem B was, I don't know. Some people said problem B was tricky to me, especially I saw in the standings also, but I could not understand why exactly. Um, I think when I explain problem B, you will see that it's pretty simple. So let's move on to problem B. Okay, so everyone focus on problem B. In fact, the name itself has the answer. So I have no clue why they put the name itself having the answer. But anyway, it says Deque process. We say that an array A of size n is bad if and only if there exist such elements such that there are 5 elements which are in descending order or 5 elements which are in ascending order. Okay, can you see here? 5 elements in descending order or 5 elements in ascending order. So if there are 5 elements consecutively which are either fully descending or fully ascending, then the array is bad, right? Yeah, so it has given an example of bad arrays. Since here you can see 1, 2, 4, 5, 6, it's bad because 1 less than 2 less than 4 less than 5 less than 6. So it's all these 5 elements are in sorted order, right? So it's a bad array. Similarly here this is bad because this is in descending order. Meanwhile here you can't find 5 elements in ascending or descending order. Okay. Now the question says you're given a permutation. You must perform n turns. In each turn you can remove either the leftmost element or the rightmost element. Okay. We can remove either the leftmost element or the rightmost element. Now choose which element to remove at each turn so that the resulting array is good. We can show that under the constraints it is always possible. Okay, we can show that under the given constraints it's always possible. So basically we have to remove L and R at each turn. Okay, so that's how the input output is there. N goes up to 10 to the power 5 normal constraints. Sum of n does not exceed 2 times 10 to the power 5. It is the input is a permutation, which means it's from 1 to n, which is all distinct. L means we remove the leftmost element, and R means we remove the rightmost element. Okay. So now how to solve this question? Um, I think the problem is trying to confuse you by making it have 5 elements in ascending order and 5 elements in descending order. Actually, it can be done much more simply. Okay. So let's say we have a permutation. I'll just give an example permutation. Example permutation. Okay. Um, 5, 3, 2, 4, 1, 6, 8, 7. Okay, so this is a permutation with total 8 elements. All the elements from 1 to 8 appear exactly once. Okay. Now, starting with this, I can remove either the leftmost element or the rightmost element at each step and place it. Okay. So one wrong way to place it would be to do something like this. If I placed, let's say I decided to place right, left, 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 or maybe, yeah, okay. So let's not take an example of a wrong way. So basically, a wrong way to place is such that if 5 elements in a row are in all descending or ascending order, then that's not a correct way to place it, right? So, okay, so how do we find the correct way to place it? So basically, at each time, if we say left, if I say left here, then it's going to place the 5, right? It's going to place the 5, and the remaining array will become this, right? Now, if I say right, it's going to place the 7, and the array becomes this, right? Now, if I write 8, then it's going to place, if I now put another right, it's going to place 8, right? And that's how the problem works. And that's what the output format means. Okay. So now in this, the crucial idea is to make this observation. Okay, make this observation. We can always choose LR. We can always choose L and R to get a alternating sequence of small and large numbers. Okay, of small and large numbers. Okay, we can always choose our L and R in such a way that we get an alternating sequence of small and large numbers. And what do I mean by alternating sequence of small and large numbers? It means that one element is small over here, then the next element is large, then the next element is small, then the next element is large, then the next element is small, and the next element is large. Okay. And by this, what happens is if we have a sequence like this, then if you take any subarray of size 5, it's going to look like this: small, large, small, right? Or it will look, if you take another subarray like this, it's going to look like large, small, large, right? So it will never be in sorted order. In fact, every subarray of 3 also will not be of sorted order, right? Yeah, B was pretty easy in my opinion. In fact, maybe easier than A also, maybe. So yeah. we just need to put it in this alternating order like this. Okay. So um, how do we do that? Okay, how do we do that? And what we're going to do basically is in our original array, we are going to maintain it like a deck. Okay, we're gonna keep it as a deck idea, store it as a deck, store it as a deck data structure. So we can access both the left and right side. Okay, data structure. Okay, so in the start, we'll put small, otherwise we'll put large. Okay, so if we have to put small right now, if small, then we can simply output, um, we can output smaller of left and right. Okay, so the small is basically a Boolean variable. We can set it to true over here. Okay, so if small is true, if small is equal to true, we can output the smaller of left and right. Okay, means the left end and the right end of the deck, and then we can pop that from the deck. Okay, otherwise we can output the larger of the left and right side of the deck, and we can output that. Okay, or larger of left and right side of the deck, and we can output that. Okay, and I'll show you with an example why this works. And yeah, at each turn we can say that smaller equals to not smaller. Like in the next step we need to output the smaller or larger. That's what we're doing. So initially small is set as true, then we do this for loop until the deck is empty. Until the deck is empty, if small is true, output the smaller of left and right side, otherwise output the larger of left and right side. And what happens essentially is, if we take this example, okay, in these two sides, which one is the smaller one? 5 is the smaller one, right? So we can output 5, which means left. Okay, now this is the remaining elements. Okay, this is the remaining elements. Now what happens? Which is the left and right side again? Which is the left and right side? This is the left side and this is the right side. We have to output the larger one of these two. Okay, we have to output the larger one of these two, which is 7. Now the remaining deck will be from here to here. Okay, now in these two we have to output the smaller one. Okay, because we're doing smaller, larger, smaller, larger, smaller, larger. So now in these two we have to output the smaller one. So it's going to be 3, right? So we'll simply output 3 over here. Okay, now our array bounds will become 2 to 8, right? This is going to become our deck. Now between 2 and 8, we'll output the larger one. Okay, so it's smaller, larger, smaller, larger. Okay, so here which in 2 and 8, which one is larger? 8 is larger. So we'll output that and pop that from the deck. So we can output 8 over here. We'll pop that from the deck. So the deck becomes like this. Okay, now we need the smaller one. Between 2 and 6, which one is smaller? Obviously 2 is smaller. So we can output 2, right? And similarly 4, 1, 6, similarly we do this process, right? So basically as we do this, we can output left and right. So since 5 was left, it will be left, 7 was right, 3 was left, 8 was right, 2 was left. So in this it's happening to happen left, right, left, right. But yeah, now in 4 and 6 we need to have the larger one. So that's going to be right, which is 6. Then we need the smaller one, which is again going to be right. And then we need the larger one, which is 4, right? So this will be the output for this test case. And what happens is this sequence is alternating between small and large, so it can never be sorted, right? I hope you understand. It will never be sorted. So that is the main idea, that we are doing alternating small and larger. And if you observe, since at each step, these two elements were compared, right? These two elements were compared, and we made sure that 5 is smaller than 7. Similarly, at this step, we had compared 3 and 7, and we had made sure that 7 was the larger one. That's why it's always alternating sequence. Okay, and it will never be sorted at any point at time. If you want me to, why Deque for simple tasks? Deque is a very basic data structure. I don't think it was complicated at all. Deque is the most, well, like, it's just a vector with 2 ends, that's all. It's not even a complicated data structure. Okay, some people have given their own test case. 1, 3, 5, 4, 2. Okay, so I'll run the test case right now. Test case. If you want to clarify the idea, you can give me your test case. I will show you how the idea works. 1, 3, 5, 4, 2. Okay. So initially the smaller one. So initially small is set to true. So we have to first put the smaller element. Okay. So we will compare 1 and 2. Which one is smaller? 1 is smaller. So the answer we want is 1 in the start, right? So the answer becomes left. Okay. The answer string is left, and the array which we are forming is 1. Now in these two, we want the larger, larger. So the answer string increases by left again, and we can add 3 over here. Now this is the remaining. Now we want the smaller one. Now we want the smaller one here, right? In these two, which one is smaller? 2 is smaller, so that's the right. So we get right, and we can put 2 in the array. Now in these two, which one is larger? 5 is larger, so we want left again. Okay, so we can put left over here. 5. Now here, whether we put left or right doesn't matter. So let's just put left, for example, and just keep it and done. Okay, so this is the solution for your test case. You can do this with 2 pointers as well, yeah. Okay, yeah, if you use 2 pointers, it's the same thing. Mostly it's the same thing. Because anyways, you need to store in a vector or array. Yeah. So let's have a quick look at the code. Uh, okay, yeah, for problem A also you can see the code. If you were confused about it, you can just pause it and see the code over here. This is for problem A. We took in the input, we sorted it in descending order, and we can sum it up and give us the answer output. Okay, so that's problem A. Problem B. Okay, so this is the code for problem B. We input n, we define a deque D. For each element x, we push it back into our deque. So this is just the input. Now this is the core idea. We have smaller equals to true. If smaller is true, then we compare which one is larger, deque.front or deque.back. We want to output the smaller one. So if deque.front is smaller, we pop that. We pop front and we output L. Otherwise, we pop back and we output R. Similarly, here we compare which one is larger and we pop the larger one and output that one. Okay. And then smaller gets flipped to not smaller. So basically this alternates between true and false at each step. And then we can see out a new line, right? So that's all the code for this problem. Time complexity is big O of n. No, we cannot sort in B. In problem B, we cannot sort because the order will get ruined, right? It has to be in the specific order they mentioned. So you cannot sort before performing the operations. Okay. So is this understandable? Any doubts, please ask it. Otherwise, I'll move on to problem C. Pairwise distinct just means unique values itself. Don't worry, it means unique values. It's a more mathematical way of saying unique values. I have never heard of deque. Then you can use 2 pointers as well. But deque data structure is like a vector in which you can do push front, push back, pop back. That's all. It's like a vector, but you can do that also. That's the only difference between deque and this. Okay, so for problem A, if you have some doubt, let me just show the code for problem A again. I think I'm not sure if I had shown the code or not. I must have forgotten, I guess. Yeah. So problem A में you have to input n and c. Then I'm sorting it in reverse order. Okay, I'm sorting the elements in reverse order, largest to smallest. If you go back to problem A, what we had discussed that we are taking the, if it's currently greater than c, we just ignore it and add answer plus plus. Otherwise, we don't do anything to the answer, but we double all the elements ahead of it, right? So that's what I'm doing here. Each element, it gets multiplied with double. If the element is less than equal to c, then nothing changes for the answer, but the future elements get doubled by 2. Otherwise, the answer gets increased. And finally, we can print the answer out. Okay, so this is problem A's code. I think I forgotten to show the code, right? This is for Shubho Mukherjee. I hope you understood. If you didn't, you can pause it and you can see. We'll move on to problem C now. Okay, problem C. I like that today's contest ABCD were very simple to code up, at least. Like the code is very small for all ABCD. And problem E1, I did not think was a good problem actually. Like problem E1 was a standard question which I'm sure I have seen before. In fact, if you Google this question properly, you will get the answer directly for problem E1. I'm surprised there were so less solves. This is such a Googleable question. Okay, let's move on to problem C. Leftmost below. Consider an array A1 to AN. Initially, the whole array is 0. You need to choose an integer x greater than minimum of A. Okay, you need to choose a minimum integer x greater than minimum of A. So this is the operation we can perform. Then I is defined as the minimum x, sorry, minimum index such that A of I is less than x. Okay. Then finally, A of I is incremented by x. Okay. So it's a bit of a complicated operation. So you need to understand, simplify. E1 is from binary search and median finding. It's a known technique, even. Anyways, so we're discussing problem C right now. Let's not get interrupted. Okay. So let's first discuss what the problem is asking us, because this operation is a bit weird and we need to understand how this operation works. Okay. So initially the whole array is zeros. Okay. Initially the whole array is zeros. And let's just take a test case from the example. Here in this test case, it says yes, right? And n goes up to 2 times 10 to the power 5, the normal constraints only. In this test case, it says yes. Okay. So that means that there is some sequence of operations such that this array can be transformed to 5, 6, 1, 1 using our given operation. Okay. So what is our operation again? We will choose minimum value. We will choose minimum value. Sorry, minimum index such that it is greater than some x. Okay, it's greater than some x. And then we will increment ai by x. And this x should be greater than the smallest value of a. Okay. So in the start, we can choose no matter what value of x we choose, right? No matter what value of x we choose, um, the value will have to go to the first position since it is a zero, right? Since it is a zero, the value will have to go to the first position. Okay. So what idea we can use is we can use this operation to make it 1, 0, 0, 0. Okay. Then we can use this operation to make it 1, 1, 0, 0, 1, 1, 1, 0, right? And then 1, 1, 1, 1. And basically what we're doing is if we use x equals to 1 for our operation, right? First we'll fill this one as 1, then we're going to fill this one as 1, fill this one as 1, and all the way till here, right? Since this is the smallest element and we want it to equal 1. So now we have seen that these two elements have become equal. Okay, we're trying to solve this example test case. We're trying to figure out how to use the opposite operation to solve this example test case. Now here we want to make it equal to 5 and 6. Okay, here we want to make it equal to 5 and 6. Also, we need to choose an integer x greater than the minimum of a. Okay, we need to choose an integer x greater than the minimum of a. So what can we do here? Yeah. So what we'll do here is we'll increase this by 4 now. Okay, in the next operation, we'll increase this by 4. And this is going to become 5, 1, 1, 1. Okay, so we chose x equal to 4, which is the first element smaller than 4 here, and we increased it by 4. Okay, now what we're going to do, we're going to choose x equal to 5, which is the first element, which is smaller than 5, right? And that is this element over here. So we increase this by 5, and we reached our target, which is 5, 6, 1, 1. Okay, so this is one way to reach our target given this operation. Okay, so I hope you understand how starting at this we reach this. So we can say yes for this. Okay, now we need to find some general pattern to find yes and no for this. Okay. So how do we approach this? Um, let's look at a no case as well. So 312 is a no case. Okay. And let's have a look why it is not possible. So we have 0, 0, 0. Okay, so this is a very constructive type of question and math type of question. So the only way you will solve it is by doing a lot of examples. Okay, so I will tell it upfront that the only way you're going to solve it is by doing a lot of examples and seeing the pattern. So it's hard to explain how to get the intuition, but when you do a bunch of examples, you should get the pattern which is going on. Okay, so now we have 3, 1, 2. Okay, and basically what we need to do is first we can do the same process again. We can make the whole array equal to 1, 1, 1. Okay, now here we need to make this element equal to 2. Okay, but the thing is, we can no longer add a 1 over here, right? We can no longer add a 1 since each of the elements is already greater than 1. Okay, and also if we try the other way, if we try to propagate 2's over here, if we try, for example, 1, 1, uh, and we try using x equals 2, well, this 2 just gets added over here. So this becomes 3. Then we use x equals 2 again, and this will become 3, which is not what we want. We want this position to be a 1, right? We want it to be 3, 1, 2. So that's why this test case is a no. Okay, basically, if we try using x equal to, it will become something like 3, 3, 0. And if we try using x equal to 1, once it reaches this position, it will stop and we can't do anything further to make this a 2, right? So that's why the answer for this test case is no. Okay. And so now in a contest to solve a question like this, you need to use some examples and try to figure out the solution. I'm going to tell you the main observations which I got after um, after looking at some examples. So first of all, um, the main observation first thing is, let our target elements be B1, B2, let's say B3, B4, B5. Okay. Then for a given element like B4, the limiting factor, okay, the limiting factor is the smallest element, is the smallest element, smallest element in B1, B2, B3. Okay, the smallest element in B1, B2, B3 is the limiting factor for B4. Okay, and the reason for this observation is basically, let's say we wanted B4 to be equal to 10. Okay, and here we had, let's say, 7, we had 9, and we had 2. Okay, so this was our array, something like this. Okay, and I'm trying to say that for this 10, the limiting factor will be the smallest element which occurs before it, because basically, like, I make the whole array into ones in my first step, right? But now, or maybe I can even make it into twos, because I can make it equal to the smallest element. I make it equal to twos. Okay. Now what happens is, um, I can make this equal to 9 also pretty easily. Similarly, I can make this equal to 7. Sorry, I can make this equal to 9 pretty easily. But the thing is, I won't be able to make this equal to 10 over here, because basically, if I try to add some number which is less than 2, right? If I try to add some number less than equal to 2, then it's going to go somewhere, like all the elements are already equal to 2, right? So it's not going to have any effect. If I try to add some number greater than 2, if I try to add some number greater than 2, then first it will get added on here. Then and only then will it get added on here. Okay. So basically what I'm trying to say is, let smallest element before a of I be a of j. Okay. Then a of j and a of I, only these two should be compared. Like, assume that they were just adjacent to each other and aj is somehow limiting ai, and we have to figure out if it's possible. Okay. So let's say aj was 3, ai was 5. is it possible? Is it possible to achieve 3 comma 5? And we can say that yes, it is possible, and I'll show you how. So first we can achieve 3 comma 3, okay? Then we can use or sorry, first we can achieve, let's say, uh so how do we make this happen? What we can do is yeah, okay, just give me a moment. I'm trying to figure out how to explain the order of operations. So we start with 0 0, and then if we do the operation with x equals 3, right? Um, what do we get? We get 3 comma 3 over here, right? Or let's say we do the operation with, so we're going to add to the first element smaller than x, right? So that's what our definition is. We're going to add to the first element smaller than x. So, right. Okay, yeah. So the way we are going to do this is we'll first make it 0. So it starts off at 0 0. Then we can make it 1 1, right? Using x equals 1 twice, we'll make it 1 1. Then we use x equals 2, right? When we use x equals 2, and it becomes 3 comma 2 since we add to the smallest element over here, right? Sorry, it becomes 3 comma 1. Now we need to use um yeah, okay. So sorry, we can make it equal to 1 comma 0. Now we can use x equals uh 2 and make it into 3 comma 2. And now we can use x equals 3 to make it into 3 comma 5, right? So yeah, it has been a while since I like did it an hour ago, so I kind of forgot the pattern. So basically this was the idea. The idea was that if we have two numbers in a row like 3 comma 5, then what we're going to do is first we're going to build the first number up, right? We can um we can just add x equals 3 first for the first number, right? We can use x equals 3 for the first number. So then it becomes 3 comma 0, right? Then we can add x equals 2 and it will go here. Then adding x equals 3 again makes it 3 5. Okay. So basically for any given pair, a1 comma a2, okay, assume here a1 is less than a2, then what we need to do is we can add first a1, we do x equals to a1, okay, then we can do x equals to a2 minus a1, and then we need to do x equals uh, a1 again, okay. So for example, it was 5 and 7, then we start with 0 comma 0, we change this to 5 comma 0, then we can change this to 5 comma 2, then 5 comma 7, okay. So I hope this is understandable how I did this, right? So basically this is the idea for the problem, is that if we have two elements adjacent to each other, we can first fill the first element right? And then we can go on to fill the next element using the values of the previous element. Okay. So now, yeah, so our original intuition was that the limiting factor is the smallest element before me. And why is that? Why is the limiting factor the smallest element before me? It's because, let's say if we had 5 comma 10. Okay, if we had 5 comma 10, then if we use x equal to 5 on 0 0, it will become 5 comma 0. Now if we use x equal to 5 again, it will become 5 comma 5. But now we cannot add any larger number over here to make it equal to 10 because it's going to get added here, right? It will get added here first. So if we try to add another 5, it's going to have no effect. And if we try to add like 6, it will first be added over here, right? Similarly, if we had 5 comma 11, we did x equal to 5. So it will go from 0 0 to 5 0. Now again we do x equal to 5, it will go to 5 5. But if we do x equal to 6, it will become 11 comma 6. Okay, sorry, it will become 11 comma 5. Instead of becoming 5 comma 11, it's going to become 11 comma 5, but because it will add to the smallest number, right? It's going to add to the smallest number. I hope that makes sense. So basically my idea over here is the limiting factor is the smallest number ahead of me, smallest number before me. Okay. And the second idea is from this observation that 510 is not possible, 511 is not possible. You can see that 57 is possible because we can add first a1, then a2 minus a1, then a1, and then it will be resolved, right? We can show that smallest number less than I at position less than I at positions less than I should be 2 times the smallest number should be greater than a of I. Okay, so 2 times the smallest number should be greater than a of I for every I. Okay, so basically when we have two numbers, let's say 3 and 4, it will work. 3 and 5, it will work. 3 and 6 onwards, it will stop working. Okay, because this element has become twice the first element. And you can show that if we have a1 and a2, then if a2 is less than 2 times a1, then and only then will the solution work. Okay, if a2 is equal to less than 2 times a1, then the solution works. Fine. Yeah, it does take some observation. Like even right now, I remembered my conclusion, but I forgot exactly what steps I had used. But yeah, practicing constructive problems helps for these kinds of questions. And so I'll show you a full test case, how to solve a full test case with this idea. So let's say we have 5, 3, 2, 1, 4, or maybe 5, 3, 4, 2, 6. Okay. So let's say we want to build this. In the start, we have all zeros. We will use x equal to 5 and we will get it as 5 0 0 0 0. Okay. Now we can use x equal to 3 and we can get 5 3 0 0 0. Okay. Now we can simply use first we can do x equal to 1 and it becomes 5 3 1 0 0, right? Now we can use x equal to 3 again. We can use x equal to 3 again. Since this is already 3, it's going to add a 3 over here, right? So it's going to become 5 3 4 0 0. Okay, so we are basically doing one step at a time. If we can't directly make it equal because some smaller number is blocking, what we are going to do is we are going to first add smaller number minus the target which I want. So sorry, my target which I want minus the smaller number. So in this case, I want this to become 4, right? But I am adding 4 minus 3, which is 1 over here first. Then I'll add 3. So it becomes 4. Okay. Can I repeat this? Yeah, I'll repeat this once. Okay. I'll repeat this once. I'll repeat the whole logic once because I think in the explanation it was not that clear, right? So I'll repeat it once. Anyways, after this, what will be the next step in this example? we have a 2, right? So simply do x equals to 2 and you will get it as 5, 3, 4, 2, 0. Now we need to make the 6, okay? But we will not be able to make the 6 over here. The reason is, if we put a 2, this is going to become a 2, right? But if we try to add any number larger than that, we try to add a 3, it's going to be blocked by this 2 and it'll get added over here instead. But we want it to add to the last number. So the answer for this is no, okay? Why is that? Because 6 equals to 6 is larger than 4, right? 6 is larger than 2 times 2. 6 is larger than or equal to 2 times 2. That's why 2 is become the blocking number for 6. Okay. So basically the whole logic, summary of the logic, So if we are making the array, and let's say I have made the values 5, 4, some 0, 0, 0, right? If the next value is smaller, then I can simply add x equal to 3 and get this value over here, right? But if the next value is larger, if the next value is like larger, I can't do x equal to 6 and get this value over here because this 4 is going to be blocking my path, right? This 4 is going to be blocking my path. So first I'll do x equal to 2. So this becomes 2. And then I will do x equal to 4. So this becomes 6. But this is not possible if the number is 8 or greater than 2 times of 4, right? Because we won't be able to add 4 2 times over here. So that's basically the summary. So the summary is, if we have a larger number after a smaller number, then it can be, or it has to be less than 2 times the smaller number to be makeable. Makeable means for the answer to be yes. For the answer to be yes. Okay. And we can write the summary of this logic in one line. We can write that basically for all I. So this is how you write for all I. For all I, a of I should be greater than minimum of a of I minus 1, a of I minus 2, and so on. Sorry, a of I should be lesser than the minimum of this multiplied by 2. Okay. So this is the condition which should hold for all I for the answer to be yes. Answer is yes. Okay. And the basic logic for this is what I did here to build the sequence 5, 3, 4, 2, 6, for example. To build a sequence 5, 3, 4, 2, 6. Observe my process. Okay. I will do x equal to 5 first. So initially, starting, we have 0, 0, 0, 0, right? Then we will use x equal to 5 and we will get 5, 0, 0, 0, 0. Okay. If you are not following along, use pen and paper and try to follow along. Now I'll use x equal to 3. Now since 5 is greater than 3, the 3 will go here, right? So it will become 5, 3, 0, 0, 0. Okay. Now observe in the next step, I can't directly use x equal to 4. Okay. In the next step, I can't directly use x equal to 4 because it will become something like this. It will become 5, 7, 0, 0, right? So that's why what I'm going to do here is I'm going to use x equal to 1 first. So it becomes 5, 3, 1, 0, 0. Then I'll use x equal to 3 again. Okay. I'll use x equal to 3 again. So it becomes 5, 3, 4, 0, 0. Okay. So that's basically the idea. Yeah, we will discuss fourth and fifth question as well. Yeah, that becomes the idea. Basically, if we have double the previous values at any point, then it's not possible. Okay. But if it's less than double, we can use this technique of doing target minus smallest. Target minus smallest we'll put, and then we'll put the smallest value again. So basically, when we put 4 minus 3, which is 1, this much gets satisfied. Then we put 3 again. and then it becomes a 4. So that's the logic over here, okay? To be honest, this problem is similar to some older problems on Codeforces. That's why I think I got it pretty easily. But yeah, the logic is a bit tricky. It's a constructive type of problem. Okay. Anyways, so if you want to see the code for this, here is the code. Okay. The code is pretty simple. Initially, we assume the answer is yes, and the smallest number I've set to infinity. Okay. Then for each number, I take in that number. If it is greater than 2 times of the smallest, my answer becomes false. And I take min and the current value to make sure that the smallest is being maintained. If the answer is true, I output yes, otherwise no. So that's all is the code for this problem. Okay. The time complexity is simply big O of n, big O of n, and the memory complexity is big O of 1. Okay. As you can see, we did not even store a vector here. We just need to know the smallest element at each point and compare it with the current element. Okay. Any doubts, please put it in the chat. I know this question is a bit constructive, so it'll be harder to understand than maybe A or B. So basically what I'm trying to say is, to make the next element, you're going to be limited by the smallest element which has occurred before. And if it is less than twice of the smallest, we have a technique to solve it. But if it's greater than twice of the smallest, you can show that it's never possible to solve it. Okay. So I'm assuming there are no doubts, and we can move on to problem D. If there are any doubts, now you can keep it at the end of the session when we will do some general discussions. Okay. Let's move on to problem D. Exorcist, I did not understand your question. Can you explain it a bit more? We are not taking till min of a of I. We are taking till a of I minus 1 itself. Because I am taking my smallest here, I'm comparing over here, then I'm updating afterwards. So essentially it is minimum till a of I minus 1 only. Okay. To be honest, this contest was on the easier side in my opinion. So maybe that's why solving 3 in 30 minutes would not give you that much rating increase. Okay. Sum of LDS. You are given a permutation such that max of Pi, comma P of I plus 1 is greater than P of I plus 2 for all I. Compute the sum of length of longest decreasing subsequence for all pairs L and R. Okay. And they have given definition of longest decreasing subsequence and goes up to 5 times 10 to the power 5 normal constraints. We need like a big O of n type of solution. Okay. So how do we solve this question? Given permutation, right? And we need to find sum over all L and R of the length of of the length of maximum decreasing sequence, right? Maximum or longest decreasing sequence, subsequence. Longest decreasing subsequence. Okay. Yeah, D was a DP question. Okay. So how do we approach this question? Let's have a look. Okay. So the main idea over here is obviously this problem would be very hard to solve without the condition, right? It's a very special condition and it has something to do with this, right? It has something to do with this condition. Okay. So given some array, given some permutation, just the whole permutation only we'll consider, okay? P1, P2, P3, P4, P5, P6, such that max of P of I, comma P of I plus 1, right? It is greater than P of I plus 2. If this condition holds, then how can we quickly find longest decreasing subsequence? Okay, how to quickly find the LDS given this permutation, okay, with this condition. And once you understand this part, we can get the whole solution almost directly. Once you understand how do we quickly find the longest decreasing subsequence in such a permutation. Okay, so we're going to try to find an example of such a permutation, or let's just take the examples they gave. We have here 6, 1, 5, 2, 4, 3. Okay, so this is the example they have given. Okay, so if we want to find longest decreasing permutation, right? Assume we're going to start at the last element. And we know that one of these two will obviously be greater than it. One of these two is going to be greater than it, right? So we will go to the one which is larger. Okay. And then again, we know that one of these two is going to be greater than it. So we'll go to the one which is larger over here. Again, we know one of these two is going to be greater. We go to the one which is larger. Okay. So we use this greedy idea. Start with last element. Always go back to previous larger one. Okay. And we can show that due to this special condition which is here, such that max of P of I plus P of I plus 1 is greater than P of I plus 2. With this special condition, using this greedy approach, we can always find the longest decreasing subsequence. Okay. So for any given permutation, obviously this technique will not work. The greedy idea will be wrong. But for this given permutation, it works. Okay. And the reason this greedy idea is working is because of this condition. Okay. And what this condition basically says is, okay, so what it basically says is, when I'm over here with only the element 3, right? When I have only the element 3, obviously that is itself the largest decreasing subsequence. Okay. Now, if I have these two elements, and the previous one is smaller, then obviously my longest decreasing subsequence will stay the same length, right? No matter which one I choose. And then since I know that for sure one of these two will be larger, I can simply jump to the larger one. Okay, so that's what the greedy idea is using. It's basically like to find. Okay, so this is a sub problem, or maybe idea for sub problem. Find LDS of permutation with the above condition, right? Of the permutation with that above condition using greedy. Okay, using greedy. And this is basically the idea. We'll start at the last element and we'll choose the previous two. And why does this work? Why does this work? It's simply because consider that we only have the last element, let's say, which is P of 5, okay? So right now the subsequence length is only 1, right? Now, let's say we have P of 4 and P of 5. Now, either P of 4 is greater than P of 5, in which case the length is 2, right? In which case the length is 2. Otherwise, P of 4 is less than P of 5. So in that case, also the length of longest decreasing subsequence is 1 itself, right? It's 1 itself. So we might as well choose this element, okay? Now, when we add P of 3, when we add P of 3, we know that one of these two is definitely larger, right? So if P of 4 was not larger, then P of 3 must be larger, and we can get a subsequence of length 2, okay? Otherwise, if P of 4 was already larger, we would have gotten this subsequence earlier, right? So that's what we're basically doing. We're doing a greedy approach. Each time the previous element is larger, we can take that, okay? If all these three were like 1, 2, 3 in like descending order, then in that case, we can simply have something like this, okay? So that's what the greedy approach is. For a permutation with this property, we can find the LDS simply by picking the next larger element each time, okay? So this is not the full solution, okay? It's just a sub-problem to find the LDS of some subarray, okay? Basically, let me write the algorithm and then prove it to you again with some examples. So the algorithm, LDS count or LDS length will be 1 and the value will be equal to the last element, okay? So let x equal to the last element, okay? Last element of the array which we want to find LDS of, okay? Longest decreasing subsequence, LDS. Then from second last element, let's say n minus 2 to 0, okay? So let me just write it like a of n minus 1, okay? So we go decreasing if a of 5 is greater than x, we can increase the length of LDS and we can set x equal to a of I, okay? And this algorithm will find us the length of LDS always, okay? For the given permutation. It won't work on any permutation, it will only work on the given permutation because of this property of P of I comma P of I plus 1 is greater than P of I plus 2, okay? And like if I try to prove this mathematically, it will take time and you won't understand much as well. So I'm going to prove it mostly with examples. So consider the last element as 7, okay? Now if the previous element is, let's say, 8, then I can simply extend my LDS like this, right? But if the previous element was something like 6, which is smaller, right? If the previous element was 6, then I don't need to start my LDS over here because I know that if I start an LDS over here, I can always extend it to 8 over here, right? Because one of these two has to be larger. One of these two has to be larger. So that's why I can always choose my last element and then continue like this. HR, do you get this idea? And anyone else who's not understanding it? We can solve it in big O and we can find LDS from the end of the array. Yeah, because x is equal to the last element. That's why we're setting it to n minus 2 over here. Because last element always we are taking no matter what, right? No matter what, this last element will be part of our LDS. We're starting from there and we are checking if this one is larger than it, then we can extend our LDS. Similarly, we can extend our LDS. So it's a greedy idea to find LDS, okay? Greedy idea to find LDS under our condition, right? So similarly, if over here it was 10, then we can again extend our LDS to 10, right? So we go from 7 to 8 to 10. Then if it was 5 over here, we will skip that. And if it was 12 over here, then 12 is greater than 10, so we can extend it like this, and we can keep going on with this approach. I hope you understand. And the reason the greedy works, the reason we can always start from the last element is we know that one of the two next elements is going to have my answer. Okay. Okay. So this is the simple subproblem of finding LDS of some permutation. Okay. Now we're going to think of how to find sum of LDS for all subarrays. For all subarrays. Okay. So right now, if you code this out, you can make an n squared solution for every possible value of r. You can go from r equals you can go from R to 0, and you can sum all the values of LDS. Okay. So we have already, using this idea, we can write an n squared solution. We can basically set, instead of n minus 1, we can set r minus 1. And basically we can sum all the intermediate values of LDS. Okay. So we can write answer plus equal to LDS. And then for all possible r values, we will do this. Okay. For all possible r values, we can run this algorithm. But then this is big O of n, and this all possible r values is also big O of n. So this solution will become big O of n squared, right? So it will be too slow, but this is why we use this. Okay, HR, if you have solved the question, that's good. I'll check if your solution is correct or not at the end. Right now, I'll just talk about the DP approach which I used for this. Okay. So now to find sum of LDS for all the subarrays, what I'm going to do is I'm going to have a DP variable. Okay. Wouldn't it be n cubed? If you do it naively, it will be n cubed. But here we can only do it in 2 loops, because basically our I can act as our L value and our R value is over here, right? So at each step over here, we can simply do answer plus equal to LDS. So it will be n squared for this idea. Okay. Vinay Agarwal. If you write, you can write it in n cube, but the way we are doing this in n squared is basically, since I is basically acting as our L value, we can simply do ans plus LDS. Okay. Or basically, let me just clear up this idea. Basically, what I'm saying is n squared solution is basically something like for all possible r values. So r can go from 0 to n minus 1, right? For all possible r values. Right? What I'm doing over here is our L value. So our LDS length is equal to 1. So we can have LDS equal to 1, x equal to a of n minus 1, right? And here we have an answer variable set to 0. Okay. Okay. So here answer can also be increased by 1 in the start itself, because we can have only one element, right? Only this LR. Then for I from n minus 2 till 0, we can do I minus minus. If a of I is greater than x, we can do LDS plus plus and x equal to a of I, right? So we're calculating the length of LDS at each step, and we can just directly add it at each step itself, right? So then this will do it in n squared instead of taking n cubed to solve it. Okay. So this is the n squared approach to solve it. Okay. Instead of finding each LR and doing the same thing, I'm just making it into one loop itself by adding the whole LDS at each step. Okay, not adding the LDS finally, I'm adding the LDS at each step only. Okay. Right? N squared is not sufficient. Yes. So we're going to improve upon the n squared solution by finding it in big O of n. And for this, we're going to use DP. Okay. So for n squared, we use the greedy idea over here. So this was a greedy idea. To convert this solution, we're going to use DP to convert it into a big O of n solution. Okay. And how do we do that? Okay. So till now, I hope you followed, because those ideas were crucial to our DP idea. If you don't understand them, you will not get the DP idea also. Okay. So what I'm going to do is DP of I equals sum of all longest decreasing subsequence LDS ending at position I. Okay. Ending at position I. So this will be my DP of I. If I compute such a table, sum of all LDS ending at position I, or basically with R equal to I and L equal to something less than I, less than equal to I, if I compute such a DP, the final answer will be simply sum of DP of I for all I, right? So this much is understandable. My DP of I is going to store the sum of LDS for each ending position, and then my answer will simply be the sum of DP of I for all I. Okay. So I hope you understand. Yeah, it's subsequence, not subarray. Sorry about that. If I accidentally said subarray, I apologize. It's supposed to be subsequence, right? Okay. So now how will we use DP to solve this? Okay. So let us consider again what we were doing. So let's say I have this array only. Let's take an example array which we had earlier. Let's say 615,243. Okay. 615,243. 615,243. Okay. Now consider at this position 4. Okay. At this position 4, if the number of LDS which are end at position 4, basically DP of I is equal to number of LDS ending at this point. Okay, ending at this point. Sorry, sum of LDS ending at this point, not number of LDS. Sum of LDS ending at this point. Okay, so what will be that sum? That sum will simply be 1, because that's simply the element 4, right? Then it will be 1 over here as well, right? So it will be 1 plus 1 plus 2, since 5 goes to 4 like this, so plus 2. The length of that LDS will be 2. Then since we can't extend 1 to 5 over here, plus 2 again, plus 3. Since 6, 5, 4 is one valid LDS. So for L equals from here to R equals from here, we get an LDS of 3, okay? So the LDS over here is 3, the LDS over here is 2, the LDS over here is 2, the LDS over here is 1, and the LDS over here is 1. So I hope you understand. So DP of I at this position will be 3 plus 2 plus 2 plus 1 plus 1. Okay, so that's how much? That's 5 plus 2, 7 plus 2, 9, right? So DP at this position is 9. Okay, now what happens when we want to calculate DP of I plus 1? Okay, if we want to calculate DP of I plus 1, well, what we know already is this is simply going to be extending each of the DPs. Okay, so each of them which ended over here, since 3 is smaller than 4, right? 3 is smaller than 4, the number of LDS which will end at 3 will simply be extending the LDS previously. Okay, so it will be extending the LDS previously. So basically the LDS values for 3 will be 4 plus 3 plus 3 plus 2 plus 2. Okay, and only 3 itself is a new LDS, so there'll be a plus 1 over here, right? So there's a 1 added over here, 1 added over here, 1 added over here, 1 added over here, 1 added over here. Why? Because all of these LDS length increased by 1, because 3 is smaller than 4, right? So if we are extending DP of I plus 1, if A of I plus 1 is less than A of I, will simply be DP of I plus I plus 1. Okay, so this is what will happen to DP of I plus 1 if A of I plus 1 is less than A of I. Okay, so all of these will be added by 1. All of these LDS will be added by 1, because all of their lengths have increased by 1, right? Now that we can use the 3, we can increase their length by 1. So all of their lengths have increased by 1, as well as we have found a new LDS, which is this one, right? Only the 3. So that's why we added another one. So this is I. We added I over here. We added plus 1. So that's why DP of I plus 1 equals dp of I plus I plus 1 in this case. Okay. Now, what about dp of I plus 1 if a of I plus 1 is not less than a of I? So if a of I plus 1 is greater than a of I, what happens in that case? So let us see our example again. For example, we have the 2, okay? So for 2, what will be the sum? Well, there can be an LDS only including 2, so that's 1. There can be 5 followed by 2, which is of length 2. Then here, there's nothing, like 1 does not increase from 5, right? So it'll be simply 2 plus 2 plus 1. Then there can be 2, 5, 2, which is LDS of length 3. So here, as you can see, it was 3 plus 2 plus 2 plus 1. And when we went to dp of I plus 1, it became 3 plus 2 plus 2 plus 1 plus 1, right? So basically, nothing changed since a of I plus 1 is greater than a of I. The number of LDS ending over here is going to be the same plus 1 because this plus 1 is always there. We get a new LDS of only including the number 4, right? Only including the number of 4 is LDS. LDS is in the question longest decreasing subsequence. Longest decreasing subsequence. That's what we're trying to find. Sum of LDS is the question only. Can you repeat? I didn't understand why we increased the value of 2. Okay, so wait, can you clarify what your question exactly is? Not very sure exactly what you're asking. So here it will be dp of I plus 1. Okay. And basically, I want you to see this example only. So it has become a bit cluttered. I'll explain this example again. We have 6, 1, 5, 2, 4, 3. Okay. And I hope you understood the n squared algorithm. So using this n squared algorithm, I'm going to come up with this technique for doing dp. Okay. And let me see, you clarified your question. Why should we increase all the values before 3 if 3 is less than 4? Okay. So here I want to find dp of I, which is sum of LDS of all elements of all, sorry, subsequence ending at I. Okay, ending at I. Fine, right? Sorry, of all subarray ending at I. Right, sorry. Right, because what we're doing is LNR is just a subarray, right? LR is a subarray. So we need to find the sum of LDS over all subarrays. So what we are doing here is basically, right. So the way our n squared algorithm worked was it found our right value over here, and then it increased our left value one by one, right? And it found the LDS value using greedy. So if we have our right value fixed here, our left value will add 1, okay, plus 1, plus 1, plus 2, plus 2, plus 3. Why is that? Because at first only this is there in the LDS. Similarly, here only that will be there in the LDS. But here 5 is greater than 4, so it becomes a plus 2. Here 1 does not change the answer. Here 6 is greater, so this becomes our longest decreasing subsequence. And so length of longest decreasing subsequence, sum of them ending at I will be 1 plus 1 plus 2 plus 2 plus 3. Okay. Now if we want to find dp of I plus 1, which is the sum of LDS ending at I plus 1, since 4 is smaller than 3, all of these LDS can be extended by one position. Okay, all of these LDS can be extended by one position. So basically the LDS will now be 6 to 5 to 4 to 3, right? So basically starting at first position, we now have LDS of length 4. Starting at second position, we now have LDS of length 3. Starting at third position, we now have LDS of length 3. Starting at fourth position, we have LDS of length 2. Starting at this position, we have LDS of length 2. So that's why we increased by I. Okay, that's why we have increased all these values by 1 exactly. And then we add another one for this newly formed subarray over here. Okay, so that's what, if the next element is smaller, we can increase the length of all the LDS by 1. And also we have to add a new one for the current thing. If the next element is larger, it's going to be the same thing, except we added a new one element for only the element itself, right? Only the element itself. That's why we did dp of I plus 1. Otherwise, it's dp of I plus 1. Okay. Okay. So basically, we converted this n squared solution to do a dp over the r values. Okay. And basically, we're saying this answer which is being computed over here, it basically depends on whether the next element is larger or smaller. If the next element is larger, we just have the previous value plus 1. If the next element is smaller, we have the previous value plus I plus 1 for the LDS. Okay. Now let's have a look at the code for this. We have n, input our permutation. Our answer is going to be the sum of all dp values. Okay. So we can do that in the end, or we can do it side by side, doesn't matter. Initially, I initialize my dp vector. dp of 0 equals 1 because when r equal to 0, then only one subsequence, right? That is the a of 0 itself, that is our LDS. So that's why dp of 0 is equals to 1 is the base case. Now for each element in my permutation, if the next element is larger than the previous element, I can do dp of I equal to dp of I minus 1 plus 1, right? Otherwise, if the next element is smaller, it's going to be dp of I equals to dp of I minus 1 plus I minus 1, okay? Now, since answer is the sum of all the dp values, I increase that by the answer. Finally, I can output it, okay? Did I get this transition from trying the example or the logic? Well, I got the n squared solution first, then I thought of some time how to optimize it. Then I got from the logic, actually, not from the examples. This question I got from the logic, mostly because I realized that if I want to extend my LDS, it's the same thing as adding plus I to all the previous ones. So I got this purely through the logic. And also it's a slightly similar idea. Like there are other questions which have similar ideas before, where we have to find how many end at R, and then we want to find how many end at R plus 1. So we will use some DP transition to find that out. So that was my idea for this, yeah, when I was doing this question. Okay. You solve on paper during contest? Yeah, I use paper, yes. I'm pretty sure almost everyone uses paper or mouse pad. No, sorry, a touchpad, something. Everyone, like most people do not have the capability to mentally solve questions of this difficulty, right? Unless you're like GM. Even GMs for hard questions will use paper. So yeah, I do write on paper to figure out patterns or whatever. Okay. So again, I repeat, this was the n squared solution, and this is how we optimized it. If you didn't quite get it, yeah, it's slightly trickier side. This question is slightly the trickier side, but it is basic combinatorics. We're trying to figure out how many LDS end at some value. As soon as you understand this greedy solution, you can see that by adding a smaller number, it adds I to all the previous LDS. By adding a larger number, it does not change the previous LDS. So that's why we get these following DP transitions. That's all. Okay. All right, let's move on to problem E. And to be honest, there's nothing much to talk about in problem E since it's already there on Geeks for Geeks. So I have no idea why they put problem E in the contest. But I will still explain the solution. But it's such a standard problem, it was already there on Geeks for Geeks. Okay, not problem E2, problem E1. E2 I could not solve, and I think there are very less solves also on E2. This is the easy version of the problem. The only difference is that we can find a subarray for the maximum submedian. What is the question? First, they define median. So there's nothing much to discuss over here. Basically, the way they have defined median means when you find the median, whichever is the larger number, right? That one is the median. So problem E. The definition of median is a bit complicated, but for the purpose of our question, we will define median like this. For a odd number, of elements, so we have 3, 5, 6, 7, 10. Okay. In that, when you sort it, it will be the middle value, right? This is the median. For an even array or even number of elements, if we have, let's say, 3, 10, 12, 14, then we can assume that 12 is the median. Okay, the larger one of the middle two elements, we'll take that as the median, because according to the definition, they want the maximum one. So that's what we can care about in this problem. Okay. For this problem, we'll just assume that the maximum one is the median. Okay. Segment tree. I don't think there's a segment tree solution for this. I'm not fully sure, but yeah. Okay. Now, yeah. So what do we need to find? What is a submedian? And according to them, submedian is simply a median of a subarray of the array. Okay. So simplification of the word submedian, it's simply a median of some subarray of the array. Okay. So submedian over here simply means submedian is the median of some subarray of some subarray of the given array. Okay, of the given array. Okay, so that's what they've defined a submedian as, simply median of subarray. And what we need to do is, yeah, and they want it to be length at least k. Okay, so k is given in the input. The input is n and k, where it goes up to 3 times 10 to the power 5. All the elements are between 1 and n. And what they're saying is the submedian should be of a subarray of length at least k. Okay, so subarray of length greater than or equal to k, right? So median of some subarray of length greater than equal to k in the given array. So simplified version of problem E1, simplified version of problem E1 is basically find the largest median of subarray of given array of subarrays of given array of length greater than equal to k. Okay, so the subarray length should be at least k. Now, actually, if you just Google this, you will get the solution. Find largest median of subarrays of given array. It's a very known problem of length greater than k. Yeah, first Geeks for Geeks article, and they have defined the whole solution over here, and the complexity is n log n. So this is basically the solution which I'm going to explain right now. If you want, you can go read this article. It's the exact same solution for this problem. Okay, and I'll explain how the solution works now. So this will not even take much time. The solution is like it's very standard problem. I'm not sure why it had so less solves. Maybe because it was at position E, that's why it had so less solves. Anyways, I don't even know why they added this question. It's such a standard one. Anyways, so um yeah, so we need to find the maximum median, right? So already from finding maximum, you should get an idea that we can do binary search. So we will binary search for the value of maximum median. Okay, for the value of maximum median. Since the elements of the array go from 1 to n, the median will also be somewhere between 1 and n, right? The maximum median will be somewhere between 1 and n. So this is our first idea to binary search. I think that is natural. If you have studied binary search, this should not be any big jump or anything. So we'll set our value of L as 1, our value of R as n, and best will be the maximum median. Okay. While L is less than equal to R. So basically binary search logic. If we can check that for the given array A, the median mid, so mid will be L plus R by 2, right? That's how binary search is defined. Mid equals to L plus R by 2. If we can check that median mid will satisfy the given condition, that we can find some subarray of length k with a median of mid. So we can write k also here in the function itself if you want. And if this is true, then we can update best equal to max of best and mid, right? Max of best and mid, and we can search on the larger values of L. So we set L equals to mid plus 1, right? Basic binary search logic. Otherwise, we set R equal to mid minus 1, right? So this is the binary search logic. Now the main thing to discuss is how to find the check function, right? How to find the check function. This is the binary search logic for it. Okay. Just a second. Right. How to check if given array has subarray length greater than equal to k with median greater than equal to mid. Okay, with median greater than equal to mid. How can we check if a given array has something like that? Okay, so let me show you. Let's take an example array. We'll take or let me just take my own example. Let's say we have uh, some array like 3, 5, 2, 2, 6, 7, 8, 1. Okay, so this is my array. And let's say I want to check if k equals to 5. So all the subarray is greater than equal to size 5. And next thing I want to check is, let's say mid equals to um, 6. Okay, so I want to know if there is some value with median greater than equal to 6 in this array. Okay, so what I will do here is I will convert values of this array into a different array. And the way I will do it is if a of I is less than mid, then b of I equals to, so this is my array A, let's say, b of I equals to minus 1. Else, if a of I is less than equal to mid, then b of I equals to plus 1. Okay, then b of I equals to plus 1. And what happens over here is this function becomes, this array becomes b of, so this is less than 6, so it's a minus 1. This is less than 6, so it's a minus 1. This is also less than 6, minus 1, minus 1. This is greater than or equal to 6. Sorry, it should be greater than equal to. Greater than equal to 6, so it's plus 1. Greater than equal to 6, so plus 1. Greater than equal to 6, so plus 1. And then here again, minus 1. Okay. Now, if any subarray greater than equal to k, size k, okay, subarray size greater than equal to k, has greater than equal to 0 sum, okay, so non-negative sum, has non-negative sum, then the check function should return yes, it's possible, else no, it's not possible. Okay, and we can do this in many ways using prefix sum, sliding window, etc., etc. Cadane, yeah, there are many ways to do it. I did it using prefix sum, and I think that's the natural approach, like easy approach for me to think of. Basically, subarray size should be greater than equal to k, and it should have a non-negative sum. Okay, in Cadane, maintaining the size greater than equal to k might not be that easy, but yeah, 2 pointers also will work. So how do we do this? And first of all, why does this work, right? Why does this work? Because -1 means a smaller number, right? -1 means smaller element, smaller element, smaller element than mid, right? Than mid. And +1 means larger element than mid. Okay? Larger element than mid. Okay? So what happens if the sum of some subarray equals 0? If the sum is 0, That means the number of smaller elements and the number of larger elements are exactly equal. In that case, we can choose this one as our median, right? And what happens if sum equals 1? That means that there is one element larger than, um, there's at least one plus one which is there extra, right? There's one plus one which is there extra. That means that the median is this value, which can be greater than equal to our mid, right? The median will be greater than equal to our mid in this case, right? So always if we can find some subarray of length k or larger, which has a positive sum, we can show that the median will be um, greater than equal to mid, right? I hope that makes sense. And how do we do this? This is again a standard problem. If maybe you have done maybe even the TLE course, I think it will have this problem. The problem is basically check if subarray has a positive sum, right? Subarray of length k. You can Google this also, you'll probably find it. Right? Sliding window and prefix sum approach. So many approaches are there. So the way we are going to do it is we're going to do prefix sum approach. And basically what we're going to do is we're going to say, so let's say we are given this array plus one minus ones, right? Okay. And now let's say my k was 5. So I will start at this position 0, 1, 2, 3, 4, right? Position 4. So this is the first subarray I will consider. And basically, the sum of a subarray, if we take prefix sums, then I'm sure if you're familiar with prefix sums, you know that the sum of subarray will be equal to sum of subarray L comma R is equal to prefix of R minus prefix of L minus 1. Okay. So sum of subarray from L to R is equal to prefix of R minus prefix of L minus 1. Okay. We want to maximize this value. Why? Because we want to find out if it's greater than equal to 0 or not, right? So it is in our best interest to maximize this value. So simply for this L minus 1, we will try to minimize this. Okay. So the subtraction part will try to minimize, and this prefix of R will try to maximize. Okay. So basically, for every valid R, let P equals to minimum of valid L minus 1, right? Valid prefix of L minus 1. And we will check prefix of R minus P. And if at any point it's greater than equal to 0, our check function can return true. Okay. So let me just write the pseudocode so you understand. So first we make the array B, right? Make the array B. Then make prefix sum array of B. Okay. Now what we need to do is and we'll have a variable which will store the minimum prefix. Okay. Now for I goes from k minus 1 till n, right? And what will this variable do? So what will this loop do? It's going to do that basically it's going to check if prefix of I minus minimum is greater than equal to 0, return true. Okay. And then minimum will be updated to min of minimum and prefix of I minus k minus 1. Okay. And why are we taking I minus k minus 1? Because like you said, window size should be at least k, right? So that's why to find, let's say from some position over here, to find the minimum prefix, the minimum values of L should be taken from here, right? The minimum values of prefix of L minus 1 should be taken from here if our window size is 5. So these can be the possible places where the prefix starts. So that's why we're taking minimum of this. So when we move this one step front, we will take minimum of this value as well. Okay, so that's how we're doing it. And this is also, I think, a known problem only. to find maximum subarray sum of some given length, right? Okay, maximum subarray sum of some length greater than equal to k subarrays, right? This is the code for that. And if none of these work, we can return false in the end. Okay, if none of these work, our check function can return false. Final note, final note. We also need to find the position. We also need to find position, or we need to find the position LR where this median occurs, right? So for that, what we need to do is, instead of returning just simply true over here, we know that the R position is equal to I, right? We know the R position is equal to I. So we can return that and we can find the L value, or we can also store the position where the minimum was found. Okay, so minimum position, and every time we update the prefix using this minimum value, we can update minimum position also with I minus k minus 1, right? So this will be the minimum position. So we can update that, these two things, and we can print our answer. Okay, so that way we will find the the maximum median, and we will also find the LNR for it. Okay, and what is the time complexity? So to find the check function is big O of n, right? Since we're not doing any sorting or anything, we're simply making the array B. We're making the prefix array B, and then we're running one loop to find if the subarray sum is greater than equal to 0 or not, right? So that is big O of n, and the binary search is log of n. Why? Because we're binary searching from L equals 1 to R equals n, right? So this was the binary search from L equals 1 to R equals n. We are doing the binary search, so it will be log of L minus R minus L, which is log of n. So the time complexity for this is big O of n. Okay, big O of n log n. Let's have a look at the code. You can also have a look at the Geeks for Geeks code. It's pretty similar. Okay, so first we take in input n and k. Here's a vector a. We're taking the input a. L and R over here is for our binary search, and best is the answer of our binary search. Okay, this L and R is the L and R for the median. Okay, L and R for the subarray median. Okay, so right now it's set to 0, 0. It can also be set to -1, -1. It does not matter. I think I'll set it to -1 for clarity. Right, this is just the subarray for maximum median of max median. Okay, so while L is less than equal to R, I will find the mid value. Then I'm using my check function over here. So the way I've defined my check function is going to return a pair, which is true or false. If it's true, it's going to return the position where the prefix started and where the median ended. So it's going to return L and R as well. Okay, so that's why I'm using this notation over here. So here's my check function. If it's true, that means this median is valid. If the current value of median is better than the best found so far, we can set best equals to mid, L equals to check dot second dot first, so the first value of the L, and R equals this. So we're finding the position where this best median occurred. Now we're simply doing the binary search logic, L equals mid plus 1. And if check was false, if check returned false, we can simply say R equals mid minus 1. Okay, so that's all the binary search logic. Finally, we'll output best, L plus 1, R plus 1. L plus 1 because it's one index, right? The Codeforces output expects one index. That's why we're doing like this. Okay. So now basically the main logic lies in the check function. What does the check function do? It takes n, the vector a, k, and mid as our inputs. It makes a temporary vector, or this is the vector b over here. And if it is less than mid, temp of I is -1. Otherwise, temp of I is +1. Okay. Then it creates a prefix array for our temp values. So our prefix array starts at temp of 0 and it increases by prefix of I minus 1 plus temp of I, right? Now, what about here? The minimum prefix is set to 0, right? So minimum prefix is simply this value mn in our logic, right? This is the minimum prefix. This is the minimum prefix position, okay? We start at k minus 1, we go to n. If the current sum is greater than or equal to 0, right? If prefix of I minus minimum prefix is greater than or equal to 0, then we can simply return true minimum prefix position comma I, right? We can return true, and this is the L value and this is the R value, where the subarray sum has become greater than or equal to 0. That means that this subarray has a valid median greater than or equal to mid, right? So that's why we're returning true over here. If this current prefix I minus k minus 1 is less than the minimum prefix, so we'll update the minimum prefix here. We'll update the minimum prefix position here as well. So go to the code for the check function. What does it return? It returns a pair of bool and pair of intent, which is the left value and right value for our current position. Okay. So that's all is the code for this problem. And even it's a standard problem. You can see other implementations on Geeks for Geeks, just slightly different. Right. So that's all. The solution to this problem. I hope this was pretty easily followable. It's just binary search and a clever check function. If you have done the basic ideas before, binary search and how to find subarray maximum, all these things are taught usually in almost any CP course or whatever. So it should be understandable, right? Okay, now I can take any general doubts or any other questions you had regarding this. Any questions regarding CP or regarding this contest, problem D, problem C? I can clear it up now. E was easier than D? Yeah, E1 was definitely easy. E2, I think they were very less solved, so no idea. But E1 was definitely easier. Again, if you have any doubts, please put it in the chat, right? Don't hesitate on anything. And yeah, I would like to remind you now there's only 3 days left for TLE's course, right? 3 days left until the end of this month. So if you haven't taken it and you're considering it, do try it out, right? Can you explain the second case of the DP in D? Okay. So you mean this case, right? Is this the case you're talking about, Vinay? Yeah. Okay, this is the case you're talking about. So let me just quickly write my example over here and show it to you. 61523 was the example we were doing, right? So 61523. Okay. Let me just zoom in a little. Okay. So this case happens when a of I plus 1 is greater than a of I. Okay. So let us find a spot in the array where that is true, and we'll see it over here. Okay. So let this be dp of I. Let us call this. Let me use a thinner pen. Let us call this dp of I. Okay. Let us call this value as dp of I, and let us call this value as dp of I plus 1. Okay. Now first I want to find how many longest decreasing subsequence end at this dp of I. Okay. So only if we have like this L equals I equals R, right? Then the longest decreasing subsequence is simply length 1, including this element itself, right? So this will be equal to 1 plus. Now this element is larger than it, so we can find a LDS like this, right? So it will be 1 plus 2, because in this the longest decreasing subsequence is 2. Now what about this? Here again the longest decreasing subsequence is 2. Why? This, right? And there's nothing better. 1 is a smaller number, so we cannot jump there. Now what about from the start of the array till here? Then the longest decreasing subsequence is 2 to 5 to 6. Okay, so this is the longest decreasing subsequence. So basically dp of I equals 1 plus 2 plus 2 plus 3, right? 1 over here, 2 till here. Similarly, this subarray also is 2. And this subarray longest decreasing subsequence length is 3, right? So 1 plus 2 plus 2 plus 3 is how much? That's 5 plus 3 or 8, right? Okay. Now for dp of I plus 1, since this element is increasing, right? This element over here is increasing. All the DPs which we had, all the DPs which we started with 5, like we had 2 to 5 to 6, right? If we start with 4, we cannot make a better answer, okay? So basically, this was the LDS we had, which we were following in the start, right? As soon as we introduce the element 4, the new LDS becomes like this. But the values itself do not change. The values itself do not change. Observe dp of I plus 1 is simply, so now if you take this subarray, the length is again 1, right? If you take this subarray, the length is 1. If you take this subarray, from 4 to 5, we can do a jump. And for that also, the length is 1 itself, right? Whether it was a jump from 2 to 5 or 4 to 5, doesn't matter. Sorry, for this, the jump length is 2. Okay, for this, the length is 2. Then from 4 to 1, here the length is also 2, right? And then from 4 to 6, the length will be 3. Okay, so this will be the answer, except now we have a new element, which is 4. So we can only have only 4 also. So that's why another plus 1. Okay, so you can observe that this is simply dp of I plus 1. Okay, basically it's the same answer as dp of I, only the only new answer which we are getting is by only including the element 4 itself. So that's all. Yeah, we just replaced 2 with 4 in this case. According to you, what is a better approach? Straight away writing the code or writing all the cases in paper, then writing the code? So the idea is basically, I think you should always write the cases on paper because, see, if you straight away write the code, it becomes very messy and then debugging might take some time, right? So if you write it in paper, then yeah, it becomes better. So I did it from my alt, but my rank was something like 400 in this contest. MacDon. I know that alts are not around on CF, but yeah, I was late to the contest, so I didn't really want to lose rating, and they don't give unrated as an option. So yeah. Okay. I missed why answer equal to sum of dp of I. Okay. So sum of dp of I, why is the answer equal to sum of dp of I? So what was dp of I? It is the sum of all LDS ending at position I. Okay. dp of I is the sum of all LDS ending at position I, right? So dp of 0 means it is sum of LDS of subarray 0, 0, right? dp of 1 is 0, 0, 1 plus 1, 1. Okay, it's the LDS 0, 1 plus LDS 1, 1. Similarly, dp of 2 is 0, 2 plus 1, 2 plus LDS of 1, 1. Oh, sorry, 2, 2, right? So that's why the final answer is LDS between all pairs L and R, right? That's why it is simply the sum of all dp of I, which is our final answer for Saikat Mandal, right? It is simply the sum of all dp of I because each dp of I means the sum of all LDS ending at a position I. That's why the final answer is sum of all dp of I. Yeah. I want to start CP. अभी तक लीड कोड किया था लेकिन CP में स्टोरी है. Okay, see, that is a skill, okay? After a while, you won't see the story much. You will get the answer. Yeah, sorry about that. Some internet issue. Anyways, yeah, so काफी बड़े don't be scared about that, right? After some time, you just need to practice reading the questions. There's nothing much to think about that. Most people, when they started CP, reading the questions would be a bit harder, right? But yeah, that's just if you do 3, 4 contests or maybe 5, 6 contests, you'll get used to it. Okay, so you usually you solve up to 1700, but you get stuck on easier questions. So for this, I can suggest doing virtual contest. Okay, do the previous contests as virtual contests. Every maybe 2 or 3 days, do a new virtual contest. Macdon, that should fix that issue. Like even I used to have that issue, but if you do the previous contest as virtual contest, that usually fixes that issue. We can optimize the space for the DP approach by storing the LDS for last index. Yeah, you can definitely. In fact, you can just not even have a DP array and you can solve it. But yeah, it will be more complicated to write. Any tip, any tip for constructive problems? The main 2, 3 tips are there, which everyone repeats, right? The first tip is obviously use pen and paper. Um, Write your observations down, right? Constructive problems. There's not much tips actually. There's just a few tips. Um, Use pen and paper. Try a lot of examples, right? Try a lot of examples and do this thing called simplifying the problem or wishful thinking. Okay, so there's this technique called wishful thinking. If you're stuck on a problem, try to solve like simpler version of the problems. Okay, so you imagine that the problem was some simpler, like the problem was very complicated. So remove some constraints. Try to solve the simple version of the problem. Maybe that gives you the idea for the full problem. Okay, so try this wishful thinking slash simplify the problem approach. Okay, and then what is and then finally practice, right? Obviously, you can only become good in problems like constructive if you do a lot of practice. Do 30, 40, 50, 100 constructive problems, depending on everyone has their own different need, right? Also, constructive I've seen helps a lot if you do math, right? So try out math puzzles in like math puzzle books or stuff like art of problem solving. Like you can do this like weekends or something like that if you're currently getting stuck a lot in constructive. So every weekend you can try some math contest problems, math puzzles, stuff like that. It helps. CP zaruri hai. See, look, to be honest, I'm still in my second year going to third year, right? So I can't tell you much about placements. Um, but nowadays in online assessments they ask. But as far as I know in coding rounds, if you have a very strong grasp of your data structure fundamentals and lead code, so you can get it. Fact 99, we have finished all questions from A to E1, and now we're just doing general doubts. So if you missed anything, you can rewind the video and you can watch it. Yeah, the main help of CP is for a job point of view, it helps you pass the interviews, that's all. But if that if you grind lead code hard enough also, you'll be able to do. So um, don't worry too much about it, okay? But in online assessment nowadays, I've seen they do ask CP type of questions. Okay, is that it? Any more questions, guys? Any more questions, chat? Yeah. Look, Pradeep, everyone has their own pace, right? I was interested in informatics Olympiad, so in 11th also I had done a little bit. Although in 11th I was still only newbie, but I never got past, I think, newbie on Codeforces. Or maybe I'd become pupil, I don't remember. But yeah, in 11th I had done some CP. That's why when I came to college, I had a bit of a head start. As a beginner, will the paid course be helpful? I think definitely because especially level 1 or level 2, because as a beginner you're not very sure what to do, right? You're not very sure what to do. So obviously many people haven't done learned by themselves. So obviously if you have monetary issues or if you feel like it's costly, then um you can, just use YouTube videos. That's also perfectly fine. Blogs and all are there. But if you feel like you want structure and you're not sure where to start, then you can try the paid course out as well, right? So I've seen the course, it's pretty good. It has organized everything well. The level 1 paid course is only 800 right now, 874. The sale is there for 3 days, so you can go check it out, right? Level 1 is for complete beginners who are just starting. Okay. If you're not a complete beginner, if you have done some lead code or something, you can start with level 2 maybe. Any suggestion to improve DP? For DP, you should first learn a little bit of the theory, and then you should try all the classic and standard problems of DP. Most of the time, 99% of the time, your DP ideas were already covered in like some classic standard problems of DP. And what do I mean by classic problems? Obviously, if you have the TLE course, then most of the classic problems are covered in the dynamic programming section, right? And also there is the AtCoder DP problems as well as CSCS DP problems, right? Most of the DP problems can be covered just by doing these. So see here, there's about 26 DP problems. The last ones become very, very hard, but at least the first 20 or first 15 you should do. As well as on CSCS, maybe the first half or first 20 problems in this. So a lot of the times the DP problems just mainly get like not repeated, but the pattern is very similar. So if you do maybe 20, 30, 40 DP questions, you can cover most of the common patterns. Especially this question was like DP plus combinatorics, slightly common pattern. I have taken Sandeep Jain Geeks for Geeks self-paced course. I have no idea about it. Sorry. I'm not sure. I've not seen Geeks for Geeks course. Okay, then I guess it's more than 2 hours. And it's getting late now. So thank you for attending the session, everyone. Hope you learned something. If you didn't understand some part, definitely do rewind the video and check it out. What else do I do besides CP? I have a few hobbies, I guess. I like read, watch YouTube, that stuff. Um, I do CTFs as well. So capture the flag competitions I enjoy personally. And I've been taking part in some hackathons as well recently. So yeah. Am I into development? When I was younger, I used to do development, like 10th, around that time. But nowadays, I do like I know development, like web development basics. I know app development basics, but I've not done for a while because not that interested. Although for hackathons, I've been doing some basic app development recently. Yeah. Okay, then everyone. Yeah, development gets kind of boring after a while. But if the project is interesting, if it's a nice hackathon and stuff, then I feel interested to do it. Yeah. All right, it's almost 1 in the morning. Um, Thank you for attending the session. Hope you learned something. If you didn't learn something, do rewind the video and watch it again. Do check out the TLE course, right? We're going to end the session now. Thank you, everyone, and bye bye.